Hi everyone. Let's go ahead and work through a challenge problem that involves our calculations of electric field. So to start, we have an arc that lies in the XY plane centered at the origin with radius r. So let's go ahead and visualize that one. And it says the arc extends from negative pi over 2 to pi over 2, so that's how I drew why I drew it how I did, measured from the positive x-axis. So this angle would be r theta. The linear charge density on the arc is uniform and given by theta, lambda as a function of theta is equal to some constant a over r sine of theta. So that's one of our charge distributions, and it is centered at the origin 0, 0. So the rest of the question then is asking if you have, in addition to this arc, some uniformly charged insulating sphere, and it's a spherical shell, of inner radius A and outer radius B. So let's go ahead and draw that structure. And it has a total charge on its shell, Q, that is equal to A over 5. And again, it was a uniform charge distribution. Then it's asking, where could I put this shell so that I could have an electric field, a net electric field at the origin equal to 0? So in order to solve this, I think the first logical thing is to find the electric field at the origin from the arc, because the arc is fixed in space. And so we will know that electric field, and then we can visualize what we're trying to cancel. So let's go ahead and do that first. So here we have I'll just actually call this the arc. And in order to do this, right, this is just a continuous charge distribution problem. We want to visualize where the arc is positive and negative. So this function sine of theta is positive when theta is in the first or second quadrant, and it's going to be negative when theta is in the third or fourth quadrant. So we end up with that charge visualization. We already know the point that we're looking at is the point at the origin. And so we see that the distance from that point to any of these charges is just capital R. We do want to visualize, though, a little dq, say, along this segment. And that dq is creating a tiny little electric field dE, and that's going to point away because it's a positive dq in that upper quadrant. So this is one dE. And then we can visualize another dq kind of symmetrically on the bottom portion in order to get an overall picture. And that's negative down there, so we're going to have a dE that points towards that dq. So what we can see here is that our net electric field is actually just going to be in the y direction because of symmetry. And so we can take that into account when we do these integrals. So we can see here that our E net is actually going to be equal to the sum of all of our DEYs. So we can sum up all our DEYs, and we just want to then write out what the y component is of each of these little DEs. So those tiny electric fields have y component contributions. A given dE, y, will be equal, it's in the negative direction, so it's negative. It'll be equal to the magnitude of dE times, and in this case, if we look at that angle, we see that we're going to want to use the angle theta that was provided. And so the vertical component there is going to end up, because that theta is also this theta, is going to be sine of theta is going to show up in that expression. In addition, we also then need to find the magnitude of dE. So here we found the component in terms of the magnitude, but we want to write out the magnitude of dE. And this is just our k dq over r squared. And we can plug in for each of these values. So we can see that dq is going to be equal to lambda ds, where ds for an arc length is equal to r d theta. So that's our dq. And again, r d theta is our arc length for an arc of charge. And r squared is the distance from dq to the point in question. So here that's just r squared. So at this point, we can go ahead and plug this magnitude in to our component, dEy, and then do our integral to find the net. So we can say that E net is going to be equal to negative, and then I'm going to have the integral, and this is going to be an integral d theta. So I want to see where my object starts and ends, and I can see that it starts and ends from negative pi over 2 to pi over 2. And so we have this situation where we could then say, okay, magnitude of dE is k lambda. I'm going to plug in for lambda with the function that was provided. So k a over r sine theta times my ds, which was r d theta, all over capital R squared. A lot of this is constant, so I'm just going to rewrite this pulling out the constants. We can also see that the capital R's on top cancels, so I end up with Ka over R squared is going to equal to the integral from negative pi over 2 to pi over 2 of sine squared theta d theta. So sine squared theta can be done as an integral, and we are just going to take the result as a given. So this is going to be equal to Ka over R squared, and then sine squared theta evaluates to 1/2 theta minus cosine theta sine theta. And then we're going to evaluate that from negative pi over 2 to pi over 2. Luckily, we can see that this isn't that messy because the cosine of pi over 2 plus or minus pi over 2 is just going to be equal to 0. And so we end up then with a pretty simple result, which is just going to be that we get Ka over R squared times 1/2, and then we get pi over 2, and then minus 0, and then minus a negative pi over 2. So this inside just becomes pi. We still have that factor of 1/2, and this ends up being Ka pi over 2R squared. And that, again, at some point I lost this negative out front. And so that, again, is going to be in our negative j hat direction. So that is a downward electric field that is from the arc of charge. We need to have that remembered as we work through the next portion of this problem. Okay, so to take a step back, we have now found that at the origin, there is a downward electric field of magnitude Ka pi over 2 big R squared, and that is from our charge, our arc of charge. So now we want to decide where can we put this structure, this shell, so that its electric field will cancel this downward area. And so what we can see is that we're going to want to place it below the origin, because if this is going to have some positive charge on it, then its electric field lines are going to be, even inside the material, are going to be radiating outward from this structure because it is spherically symmetric in a angular way, and so there's no angular dependence, and the electric field will radiate outwards. So we need an upward arrow to cancel out our downward arrow. So we're going to have the electric field from the arc pointing down. So we need to have the electric field from the shell pointing up in order to cancel that. So now the question is, if we know we're going to put the shell below so that the center is below the origin because of the direction, we now need to figure out how far. In order to figure out how far, we note that we need the magnitude of the electric field from the shell to equal the magnitude of the electric field from the arc. So now we have a problem where we want to find the electric field from the shell as a function of r. And this is a very typical Gauss's law problem. So let's move on to looking at the electric field from the shell. I am going to start a new page to do that. So the electric field from the shell, we can say that first of all, we know that if it has an inner radius A and outer radius B, and again, the total charge Q was equal to A over 5, that was given in the problem statement. So then we can say that the electric field for R less than A inside the hollow, the electric field is equal to 0 because the Q enclosed is equal to 0, right? So that's not going to be a location that's going to help us in this problem. And so what we can say then is that we're going to look in two locations. We can look for the electric field for R greater than B, that's going to be outside. And we can look for electric field in between, because if there's a solution, there's very likely going to be two solutions. And that's going to be because if we look at the electric field as a function of R for what we're just expecting, even just knowing some basics about the charge distribution, we know that inside the hollow area, it's going to be 0. But then as I start to extend into the material itself, I'll be enclosing more and more and more charge. And so the inside, in some fashion we haven't yet calculated, will increase as I'm enclosing. Q enclosed gets bigger and bigger. So it's going to increase all the way up until I get to R equals B. And then outside, remember that spherically symmetric charge distributions just look like point charges when you're outside of them. So then it's going to drop off outside just like a point charge. So if we're trying to find some magnitude of E, and if this is here my magnitude of E, we want to find some value where this is equal to the E from the arc, we can see that we're going to get one value very likely inside and one value outside as well. We might have the very rare situation where we get exactly one value. Or we might get an invalid equation, in which case there is no value and our electric field from the shell is just simply not strong enough to cancel the electric field from the arc. So we'll have to follow the equations and maths and see where we end up. I'm going to start with the outside first because it is the easier version of Gauss's law. So if we look here with R greater than B, so now I'm enclosing the entire shell. So if I draw my Gaussian surface and I can visualize the charge enclosed, I'm enclosing the whole thing. So my charge enclosed is simply my total charge, which in the problem was given to me as A over 5. So I can do my integral E dot dA is equal to Q enclosed over epsilon naught. And remember that with this integral, the left-hand side of Gauss's law for spherical symmetry reduces to E times 4 pi little r squared, where again, that is the surface area of the Gaussian surface through which we're looking through the flux. And as a quick reminder, that is because the electric field and the area vector, so my dA vector being perpendicular to that spherical Gaussian surface, and my electric field vector are parallel. So E dot dA goes away, right? We have that E dot dA disappears in that dot product, and so that goes E, magnitude of dA, and then the cosine of the angle between them, which is just cosine of 0, and so then that allows me to say that this is then equal to 1, and so E dot dA, the dot product goes away, I get E times dA. And then the second reason is that every little dA on the surface has the same magnitude of E because it is symmetric. So we can say and, so this is a key point, that their E and dA are parallel everywhere on the surface, and the magnitude of E is the same for all parts of the dA, all of the dAs on the surface. And so that allows us to take the E out of the integral. So E dot dA turns into integral E dot dA equals integral E dA, that was the parallel components, and then the electric field comes out of the integral, and we end up with just integral of dA. And again, that is the surface area of our Gaussian sphere, adding up all our dAs around that Gaussian sphere. So that's a summary as to how that left-hand side simplifies, and I will mark that here. This is how the left-hand side of Gauss's law simplifies. And that's something that's important to really understand and be able to visualize. Okay, so back to our original problem. Once we know that the left-hand side can be written in this nice, simple way, we can then say that E times 4 pi r squared equals, and then my Q enclosed was A over 5 over epsilon naught. So here I get my electric field as a function of R is 1 over 4 pi epsilon naught times, and in this case, I just get A over 5 little r squared. And I'm going to rewrite this because our arc was in terms of K. I'm going to rewrite this result in terms of K as well, because 1 over 4 pi epsilon naught is K. So those are sort of interchangeable. And so we have Ka over 5 little r squared. And so that's going to be my electric field when I'm outside the shell. So if we have that electric field outside the shell, before we solve for the inside, why don't we at least see if we have a result, right? Because again, we might have no valid results in this scenario, depending on what our value of charge on the sphere was. So let's go ahead now and say that we want, remember, we want the magnitude of the electric field from the arc to be equal to the electric field from the shell. So we're going to say the electric field from the arc, recalling our previous result, Ka pi over 2r squared, and now we're just doing magnitudes. So the magnitude of the E from the arc is the Ka pi over, and I believe that was 2r squared, is going to be equal to the E of the shell, which then that's going to give me my Ka over 5 little r squared. At this point, I can see that my K's and my A's cancel, and I'm left with a pretty nice result, which is simply that my little r is going squared is going to be equal to my 2 capital R squared over 5 pi. And so we have this good result for our electric field from the shell being equal to the electric field of the arc at R equals the square root of 2 over 5 pi times R. This result ends up being approximately equal to 0.36 times R, which is valid because we can see that this is in fact going to be greater than the radius of the shell which we were provided, since we were told here that our outer radius of this was equal to 0.3 R. So if we had gotten something here that was not valid, then we would know that we would have no potential result. But because we do have a value which is valid for outside of the shell, because it is indeed outside of our outer radius that was supplied, then we have a valid result that is correct. So one solution is to have our arc with the origin and then a distance of square root of 2 over 5 pi r below it. We would put the center of our shell, and the shell is much smaller than the arc, so it would go into that space and create an electric field at the origin such that the electric field from the arc exactly cancels the electric field from the shell. So we have one solution, and now it's just a matter of looking at another solution. Again, if we have a solution for outside, there's going to be another solution on the inside as it grows to that point. So now let's figure out the electric field on the inside of this shell. So the electric field on the inside, so that's going to be on the inside the material of the shell. So R between A and B. I want to draw again my Gaussian surface. So here's my charged object, and I'm going to shade in some radius r. Remember, the object itself has some inner radius a and then some outer radius b. And now we'll use these values, 0.1 r for the inner radius and 0.3 r for the outer radius. And the charge enclosed by some Gaussian surface of radius r is going to involve that volume. And so what we have to do is we have to say, okay, I'm going to take our left-hand side equal to the right-hand side. The left-hand side is just E times 4 pi r squared. All the reasons I talked about previously are still valid because it is just involving the Gaussian surface, which doesn't change no matter what it's enclosing. And then that's going to be equal to my Q enclosed over epsilon naught. And so now I have to decide what my Q enclosed is. So Q enclosed in this region that is enclosed by the Gaussian surface is going to be equal to my total volume charge density times the volume that's enclosed. And so that can be written as my Q total, which was A over 5, over my total volume. And the total volume of the sphere is going to be 4/3 pi outer radius cubed, b cubed, minus 4/3 pi inner radius cubed, because that's going to be taking the full volume and then minus the whole. So that is, this first term is my volume charge density. So that's my volume charge density. And then I would have my volume enclosed, and my volume enclosed is simply going to be equal to 4/3 pi, and it's going to be little r squared, because little r cubed, because now I'm only going to the Gaussian surface, and then still I have to subtract off the whole, so 4/3 pi little a cubed. So that's going to be my volume enclosed in that area. So those combined give me my Q enclosed, so I can write out the somewhat messy result as E equals, and then I'm going to say 1 over 4 pi epsilon naught, and I'll keep that 1 over r squared here as well while I write out this kind of messier result. I have an A over 5, and we can see that my 4/3 pi's cancel because it's in every term. And so over here I do end up with an r cubed minus a cubed all over a b cubed minus a cubed. So at this point, right, this is essentially the electric field inside the material, right? For between the radii between A and B. So that's inside the material for the shell. And so we can take this and we can set it again equal to the magnitude of the electric field from the arc. And so if we take this statement and we just copy it down, and now we can set that equal to our previously found arc, which was Ka pi over 2 capital R squared. And again, we're just setting magnitudes equal to each other so that they can cancel out. Then I do have an equation that I can solve for pi. It simplifies, it's for r, I'm sorry. I could solve it for little r. And it does simplify a little bit because that 1 over 4 pi epsilon naught is in fact k. So I do have some cancellations of my k's and my a's just as before. But ultimately what I'm going to end up with here is a cubic equation for r, right? I am fundamentally going to end up with something that is a cubic equation for R. And so I am going to simply just use a computer to solve that. I can use Wolfram Alpha in order to solve it, for example. And when you solve this, you end up with R, in this case, being approximately equal to 0.224, I will say, times R. And we can check that this is in fact in between our inner radius and our outer radius, because we know that that's from 0.1 to 0.3. So it is in fact inside the material as expected. So we have two locations where we could put our position. The final answer to this question would be that we would place the shell, the center of the shell. So it's at x equals 0, z equals 0, because we do have 3 dimensions here. And then these two y values, y equals negative, remember we're placing it below, so negative 0.224 r. That is when it's going to be in the center of the, canceling it out from the middle of the material, the electric field in the middle of the material. And then this other result, which was also still when we placed it below, and that one was 0.36 r. So this problem combined a continuous charge distribution with Gauss's law, so a spherical shell. And so individually, those are very manageable problems, and we put the concepts together. The math gets a little bit messy, but hopefully the concept still makes a lot of sense. And we have these very valid results, which hopefully also make a lot of sense. I hope this helps.